One of them, I don't know.
Okay, you're all set.
All right, thank you. All right, welcome everybody. Thank you for coming to this interdisciplinary seminar. It's my pleasure to welcome among us here Dr. Li. Dr. Husheng Li is from University of Tennessee in the Electrical Engineering and Computer Science Department. Dr. Li received his BS and MS from Tsinghua University in China in 98 and 2000 respectively, and he got his PhD degree from Princeton University in 2005. He joined Qualcomm in San Diego as a senior engineer where he performed research in wireless communication, and now he's pursuing his interests in statistical signal processing and communications and information theory at University of Tennessee in Knoxville. It's a pleasure to have you here. Thank you for coming. The floor is yours.
Good afternoon, everyone. So thanks for coming to my presentation. The title of my presentation is a multi-user detection debt and the linear suppression of the intercarrier interference in OFDM systems. So this is an overview of my presentation. Since my talk concerns with multi-user detection, I need to do a very brief introduction about multi-user detection and CDMA systems. Then I will apply the multi-user detection in OFDM systems. So first we will discuss a little bit about the OFDM signal model, and we convert the OFDM system to an equivalent CDMA system. Then we can apply the techniques of linear multi-user detection to OFDM systems. And then we will discuss the performance of systems with perfect channel state information or without channel state information. And finally, I will give some numerical results. So first, since we are discussing multi-user detection, we need to define what multi-user detection is. So actually, as many of you guys know, multi-user detection is a technique to suppress the multiple access interference in CDMA systems. So it is more than 20 years old. It was originally proposed by Professor Sergio Verdú in his PhD thesis. The title is Optimal Multi-User Signal Detection in 1984. So this is a picture of Professor Verdú. So here I list some milestones of multi-user detection. So as we know, in 1984, that is the birthday of the multi-user detection. Then in 1989, people proposed linear multi-user detection because the original multi-user detection is a non-linear one. It is optimal. In 1995, people proposed adaptive multi-user detection, and it could be blind. That is, you need not know the information about the spreading code. After 1998, people paid more attention on the nonlinear interference cancellation by using the feedback from the output of channel decoders. And in 1998, we have the book that is a Bible in the community. It is a multi-user detection written by Professor Verdú, and I can remember how much time I spent on the problem set on this book. So that is a very nice book. In 1999, people applied the turbo principle on multi-user detection. In the same year, Professor Verdú applied the theory of random matrices on the spectral efficiency analysis of multi-user detection. This side.
Noise in the audio. Can you stop and try to fix that?
Okay, thanks. And in 2002, Tanaka, a Japanese physicist, applied the technique in statistical mechanics to get the asymptotic explicit expression for the performance of optimal multi-user detection. Then people have a full understanding about the performance of multi-user detection. So those are some milestones of multi-user detection. And here we can see a lot of honors received by the multi-user detection guys, especially in 2000. Both the Best Paper Award in Communication, Society, and Information Theory was awarded to people working on multi-user detection. So this is a very prestigious research domain. So why we want to do multi-user detection? First, we need to know a little bit about CDMA system. So this is the signal model of CDMA system. So this is a received signal, that is a vector. This is a spreading code. SK is a spreading code for user K, and XK is the channel symbol for user K. And we know N is a noise. So if the SK, the spreading codes, are not orthogonal across different users, then there exists multiple access interference across different users. So in CDMA systems, in the uplink, it is because the MAI is because of asynchronous transmission, because we know in uplink systems, the transmissions are asynchronous. And also because of the multipath fading. In downlink, it could also be caused by the multipath fading. So we have three types, or we can have several types of linear multi-user detection. So the first one is matched filter, which is widely used in most practical CDMA receivers. And actually, in the matched filter, you are not using the spreading code of other users. You're just regarding the interference as noise. So then you are losing information. Then we can use a better detector. It is a decorrelator. If there is no noise and the number of users is smaller than the spreading game, then you can perfectly remove all the interference. But since in practical systems you always have noise, then we can use linear multi-user, LMMSE multi-user detection. And you can look up the details in Professor Verdoux's book. And for the CDMA system, we can measure the performance by using, say, capacity or spectral efficiency or throughput or bit error rate. But all those measures are common for all communication systems. So here, for the multi-user detection, we use two types of special measures to evaluate the performance. The first one is called multi-user efficiency. Actually, it is a ratio between the output SNR and the input SNR. So we can see this ratio is always smaller or equal than 1. When it is equal to 1, that means there's no impact of interference. That means the multi-user system is equivalent to a single-user system. And another measure is asymptotic multi-user efficiency. So that means we just let the noise power turn to 0. That measures how the multi-user detection performs in the high SNR region. So these are just some common sense about multi-user detection. So once we get the multi-user efficiency, then we can convert the multi-user system to a equivalent single-user system. In such a single-user system, the transmit power is just scaled by this scalar, the multi-user efficiency. So if this multi-user efficiency is small, that means your power, your equivalent power is smaller. So next, we discuss how to apply the multi-user detection in OFDM systems, because it is well-known. It is pretty well known about how to apply the multi-user detection in CDMA systems. But maybe it is pretty interesting to discuss how to apply it in OFDM systems. So first, we need to discuss what is OFDM. So now, we know CDMA is being replaced by OFDM. OFDM is orthogonal frequency division multiplexing. So actually, OFDM is not a young guy. He's more than 40 years old. It was born in Bell Labs in 1960s. But John Lennon told us life begins at 40s. So although OFDM is 40 years old, it is flourishing. So now it is becoming the dominating technique of 4G systems, say WiMAX or LTE. LTE is being developed by 3GPP organization, or UMB, which is being developed by 3GPP2 organization. So now we are facing a problem. Is multi-user detection dead? Because we know CDMA is no longer spreading, and OFDM is hopping everywhere. So where should the multi-user detection go? You know, there is an old Chinese saying, where should the fur attach if the skin is gone? So now we want to discuss, is multi-user detection dying? Here I dropped a figure. This shows the number of papers about multi-user detection published in IEEE transactions on wireless communications. So we can see in 2004, there are about more than 35 papers on multi-user detection. But this year, only 10. So we can see a sharp decrease here. So does that mean people no longer need to study multi-user detection? But the answer is no, it is still being alive. So why multi-user detection is still alive? Because essentially multi-user detection is dealing with vector channels. Here we can define the vector channels as a information symbol is represented by a vector. We know CDMA is a vector channel because one information symbol is represented by a bunch of chips. So that is why CDMA system is a vector system. But we can have a lot of examples of other vector channels, say CDMA or MIMO system, because MIMO, you have multiple receive antennas. Then if you send out one symbol, then actually you are receiving a vector. Or TDMA systems, but maybe the TDMA has a dispersion. Then actually you are dispersing your information into several dimensions. So that is also a vector channel. Or OFDM system with frequency dispersion. But maybe you will ask this question. Maybe you have learned a lot of stuff about OFDM. You know that actually OFDM system is a scalar channel because one data stream is sent out within one subcarrier. So actually that is a scalar channel. How can you say it is a vector channel and we can apply multi-user detection to OFDM systems? But the reason is we're dealing with non-ideal systems of OFDM. If in non-ideal systems, in non-ideal situations, there exists intercarrier interference in OFDM systems, then the ideal scalar channel becomes a vector channel. So the intercarrier interference could be caused by, say, Doppler shift, that is the time variation of the channel. Or the frequency shift, if the alignment of the frequency of the transmitter and receiver is not perfect, you have some frequency shift. This could also cause interference, intercarrier interference. Or time domain synchronization error. If you have time synchronization error, maybe you can use MATLAB to do a simple simulation. Then you will see a dispersion of the information into several dimensions. So actually there are many people working on how to suppress the interference in OFDM systems. So here I listed a bunch of papers. But here we focus on only the inter-channel interference caused by the time variation, or equivalently the Doppler shift. And actually, we have submitted this paper to IEEE transactions on signal processing. So next, we want to look into more details about the OFDM systems. So this is a simple illustration of the OFDM Tranceiver. I guess maybe many of you guys have known more details than I. So at the transmitter, the data stream is converted from serial to parallel with. Actually, this is in the frequency domain. Then we do a IDFT to convert it to time domain. Then we pass it through the channels, wireless channels. Then at the receiver, this is a received symbols in the time domain. Then we do a DFT to obtain the frequency domain signal. And finally, we convert the parallel frequency domain signal to serial data streams. Then we can recover the original data stream. So that is how the OFDM transceiver works. And this is the channel model of our OFDM system. So suppose the system is operating over a multipath fading channel. Suppose we have L paths. And we denote the channel gains and the channel delays by these two notations. Here, HT L means the channel gain at time slot T and for path L. And this is path delays. Then we can represent the received signal by in this way. Here, the T is the noise. So now we have got the received signal in the time domain. Now here the question comes, how can we get, if we are given the X, the time domain input signal, and the channel parameters are also provided, then how can we compute the explicit expression for the frequency output, and how can we explain the ICI here? Actually, this is a question when I was in Qualcomm, when I was interviewed many interviewees. This is an interview question. And it is a little bit disappointing that none of the interviewees give me a satisfying answer. And the best answer from a Caltech guy is he just he began to deduce the expression for this from the very beginning. And he's very good at math. And finally, he gave me a perfect answer. But that is not what I want. I just want a very simple deduction of expression for the frequency output. Now, actually, this is a very simple question, because if you can recall the important relation between the time domain and frequency domain in DFT, you can remember that in time domain, the multiplication in time domain is equivalent to a circular convolution in frequency domain. And we can see here, actually it is a multiplication. Then we can just use the circular convolution to get an expression for the frequency domain output. Here, H is the DFT of the channel parameters, and X is the DFT of the input signals, and Y is the frequency domain output. W is the noise in the frequency domain. So here is the lesson. If you go to Qualcomm for interview, do not think the question is very complicated. You can always find a very simple way to solve it. So as we know, the convolution always diverse. It always diverses the power into many dimensions. Then we get a very intuitive explanation here. Why there is ICI in the why there is an intercarrier interference in the OFDM system. It is because of the convolution, circular convolution. And actually it is due to the time selectivity, because we know in the frequency domain, if there is a frequency selectivity, that means you have multipath fading, and the channel is frequency selective. Then we have intersymbol interference in the time domain. Now, in the dual domain, if we have time selectivity in the time domain, we will have interference in the frequency domain. So actually, this is a very simple explanation for the intercarrier interference caused by time selectivity. So this is just the intuitive explanation. But now we are facing a problem of how to convert the OFDM system into a CDMA system, because we want to apply the multiuser detection technique. Actually, this conversion is pretty simple. We can just regard each subcarrier as a virtual user. So suppose this is a baby OFDM system. Suppose we have only 4 subcarriers. We can regard them as 4 users. But since there is a dispersion, the signal of each user is represented by a 4-dimensional vector. Then at the receiver, all the vectors are superimposed with each other. And this is very similar to a CDMA system. Then we can do some more formal computations. Here I just copied the circular convolution for the OFDM system. Here Y is the frequency domain output, H is channel, X is the input, W is the noise. Actually, we can rewrite it into a linear transformation. Again, Y is the frequency domain output, and S is a spreading code matrix, equivalent spreading code matrix. And X is the input. Again, X is the input. And the case column of matrix S is the equivalent spreading code of virtual user K, or equivalently, the subcarrier K. So we can take a look at the expression for the spreading code matrix. So this column is the spreading code for user 1. This column is for user code the spreading code for user 2. So this looks a little bit complicated. We can see nothing from it. But later we can find some interesting properties from this matrix. So this slide shows similarities and the difference between the traditional CDMA system and the CDMA system born from the OFDM system. So similarities, both are vector multiple access channels, but there are a lot of difference. For the traditional CDMA systems, the elements within a spreading code are mutually independent because we are using random spreading code. But in the CDMA system born from OFDM systems, the elements are mutually dependent. Then this means we can no longer use the theory of random matrices to analyze the performance of the CDMA system born from the OFDM system. The second one is for traditional CDMA system, the power is spread over all the dimensions of the spreading code in a uniform way. But in the CDMA system born from the OFDM system, actually the power is quite focused on one dimension, and it is dispersed into other dimensions in something like exponential way. And in traditional CDMA systems, the users could be asynchronous, but in the OFDM-based CDMA system, it is always synchronous. And for the OFDM-born CDMA system, the system node, which is defined as the ratio between the number of users and the spreading gain, this system node is always 1 because we know the spreading gain, spreading gain actually it is equal to the dimension of the vector. It is the number of the subcarriers, but the number of users is also the number of subcarriers. Then the spreading gain is always 1. But for the traditional CDMA system, the system node could be any arbitrary positive real number. So that is a larger difference. So next, we will discuss how to apply the linear multi-user detections in OFDM systems. So the output of a linear detector, say for user K, is given by this expression, this general expression. Here, the vector Vk is the linear detector for user K. So we consider only 3 types of linear detectors: the matched filter, traditional filter, and LMMSE detector. And we will explain them in the following slides. The first one is matched filter. Actually, it is widely used in traditional CDMA receivers. The feature of matched filter is it considers the interference from other users as Gaussian noise. Then actually we are losing the information of spreading codes of other users. Then the matched filter is simply given by here the detector Vk is just the spreading code of user K. So this is pretty simple. And we call this filter as a traditional filter because it is used in almost all OFDM receivers. Actually, for this filter, we are just picking the signal on the desired subcarrier. And we do not consider the signal on other dimensions in the focus domain. Then this traditional filter is given by this expression. Here, 1k means it is the almost 0 vector, and only on the case, only the case element is 1, and all the elements are zeros. So this is pretty simple.
So it's not that different than from the previous one. What's the difference?
Here,
Yeah.
this one is a actually it is a maybe I can write down with this blackboard. Suppose we have a random matrix, we have a spreading matrix. Say this is a case spreading case column. That is a spreading code of case user. Here for matched filter, the linear detector is the column, the case column. So that is a matched filter. Then for the traditional filter, actually we're just taking out SKK here. Then the VK is just given by so there's only one element is non-zero. Actually, this is the traditional filter is how OFDM receiver does. For LMMSE multi-user detector, actually it is a good trade-off between the complexity and the performance, because since it is linear detector, then the computational cost is much lower than the optimal one, but the performance degradation compared with the optimal multi-user detection is not so much. So in the LMMSE multi-user detector, it considers the information of the noise power and the spreading code of the interferers, and its expression is given by this way. So you can look up how to derive this expression in Professor Verdoux's Bible book. And for LMMSE multi-user detector, the output SNR is given by this expression. Actually, this is a problem in Professor Verdoux's book, and that is one of the homework when I took Professor Verdoux's course, and I spent a lot of time to derive this expression. And the asymptotic multiuser efficiency is given by this expression. Here R is the spreading code, is the covariance matrix of the spreading code. Actually, it is defined as, I guess I defined it in the previous slide. Oh, not. R is defined as R equals the transpose of the spreading code matrix times the spreading code matrix. So the asymptotic multiuser efficiency is uniquely determined by the covariance matrix. So we will use this property later. So next we'll analyze the performance of systems in systems with a perfect channel state information. So this is a pretty ideal case, and it is impossible for practical systems, but it can provide some insights for us. So first we assume the channel is frequency flat. That means there's only one path. And then we have a n-1 channel gains. Here n means the number of subcarriers. Also the number of time domain chips. We define the average channel gain as, we denote it as a h bar. The average channel power gain as g bar. The channel gain variance as this. Channel power gain varies as this, and we denote the kurtosis of channel gain by kappa. So here are just the simple notations. Then when L equals 1, then the spreading code matrix is given by this matrix. Then we can observe that actually it is a circular matrix, because we can see in the first column it is H0, H1, Hm minus 1. And in the next column, actually we are rotating this column, because we put this Hm minus 1 here, and H0 is rotated here. So actually it is a circular matrix. Then we can apply a very interesting property of circular matrix, because we know if you can look up any book discussing matrix theory, we know any circular matrix can be decomposed in this way. And here the U is given by this expression. Here W is defined as, actually that is a factor of, it is defined as a factor of 2 pi j over n. That is factor of DFT. And this matrix lambda is a diagonal matrix. And the one interesting thing here is the diagonal elements of this the matrix lambda is the diagonal elements of this matrix are the channel gains in the time domain. Then we can see actually such a decomposition is a DFT transformation, because we can see in the matrix S, the first column is the DFT of the diagonal elements in the matrix lambda. And the diagonal elements in the matrix lambda is the IDFT of the first column of matrix S. So this is a very interesting property for the circular matrix, and we will apply this property later. So using some boring computation, we can obtain the multiuser efficiency of the traditional filter. It is given by this expression. One interesting thing is it is impacted by the variance of the channel gains. And we can compute that the asymptotic multiuser efficiency for the traditional filter is 0. That means in the high SNR regime, such a traditional filter is very inefficient, because if you input infinite power, you can only get finite SINR or finite channel capacity. Then you are using infinite source resource, but you get only finite reward. Then the transmission is very inefficient.
So isn't this similar to what people? I guess maybe Brian would be better placed for. Isn't this similar to what the spatial temporal codes? I mean, isn't that what they're trying to kind of spread the information across?
I guess I haven't thought about. Maybe that's a very interesting question. I haven't thought about the spatial code, okay. But there may be something hidden behind this. There could be some relation between the discussing here and the spatial code.
Question.
Yes.
What you have there is the traditional filter. Doesn't have any kind of equalization in it, right?
Equalization?
Yeah, the usual ways that ICI and ISI are addressed in OFDM systems is usually through some kind of frequency domain or time domain equalization.
Yeah, actually, the multi-user detection here is I can say it is a type of equalization. Right. Because here we are also try to suppress the intercarrier interference. And that is the same thing as the equalization do.
Right. So, yeah. but when you talk about the traditional filter, you're not talking about a traditional OFDM system, right?
Actually,
which would include frequency domain and time domain equalization.
Actually, here the traditional filter is not doing equalization. It's just the simplest way to. It's the simplest way for the OFDM system. It may be interesting to compare the multi-user detection approach here with some other traditional equalization.
Have you done that?
Maybe that is a next step. Maybe that is the next step. Because we are looking at this system from the viewpoint of multi-user detection. Maybe in the next step or in our next paper, we will compare the traditional equalization with the multi-user detection here. So that may be a very interesting topic. And for the matched filter, we can also obtain the multi-user efficiency here. And one interesting thing is we can see it is impacted by the kurtosis of the channel gain. And again, the asymptotic multi-user efficiency is still 0. That means you have a very inefficient transmission in the high SNR region. But now we can analyze the performance of the LMMSE multi-user detector. And as shown in previous slide, the output SINR is given by this expression. And we can decompose this matrix into this quite complicated matrix. Now we can apply the DFT property here. We can do some comparison. So this is the decomposition of the spreading code. And as we can recall, the first column of this matrix S is the DFT of the diagonal elements in this matrix lambda. Then we can do the same thing for this decomposition. Similarly, the first column of this matrix should be the DFT of the diagonal elements in this matrix. And the diagonal elements in this matrix should be the 0 frequency element component of the DFT of this diagonal elements. Then we can obtain the diagonal matrix, the diagonal elements in this matrix is given by this expression. That is just the sum of the elements, the diagonal elements in this matrix. Then we can get this quite complicated multi-user efficiency expression. since it is too complicated, then it is pointless to look into the details. But we can get a very interesting result for the asymptotic multi-user efficiency. If we let the noise power in this expression turn to 0, then we can get this expression. If you took a few seconds to read this expression, you will see that this expression for the asymptotic multi-user efficiency is just a ratio between the harmonic mean and the arithmetic mean of the channel power gains. So from middle school math, we know the harmonic mean is always smaller than the arithmetic mean. That means this expression is always smaller than 1 or equal to 1. And one important thing here is the AME is no longer 0. That is different from the traditional filter or matched filter. Then this means if you put infinite power into the system, then you can get infinite output. You can get infinite throughput. Then this means this transmission in the high SNR region is pretty efficient.
So that's basically the effective what it's called in statistical linear algebra, the effective rank of your channel covariance matrix. Because when you take the arithmetic and the geometric ratio, it determines the number of principal components in your covariance matrix.
Yes, that may be an interesting explanation for intuitive explanation. Maybe I can add your word into my revised version of my paper. As for the multipath case, then it is the analysis is much more complicated. So we can just give some qualitative conclusion here. So we have several assumptions. We only analyze the LMMSE multi-user detector. Suppose we have only 2 paths, and the first path dominates. That means most of the energy is given in the first path, and we assume the fading is very slow, because if for fast fading, then it is sensitive. It is pointless to do coherent detection. Then we can, after some computation, we can get some qualitative conclusion. That is, if the phase of the 2 paths matches, then the AME is increased compared with the single path case. If not, then the AME is decreased compared with the single path case. Actually, this is very intuitive. If the phase of the 2 paths match with each other, then actually we're enhancing the signal. So this is pretty simple. One important conclusion is if we have one additional path, to the first pass, then the additional pass helps or impairs the AME in equal probability way. So it may be better or it may be worse, and the probability is the same. Next, we discuss the systems without channel state information. So first, we suppose we have some channel state information in the time domain. We have some channel estimate in the time domain, but they are not perfect. And we assume, for simplicity, there's only one path, and we denote the channel estimation error by this expression. We assume the channel estimation is unbiased. This is a reasonable assumption. And we assume the channel variance is pretty small. If it is large, then the whole system just collapses. And the number of subcarriers is sufficiently large. For a typical OFDM system, it could be 1024 or 512 subcarriers. And we assume the channel estimation errors are ergodic. So these are just assumptions for the analysis. Then we can obtain the performance of the traditional filter and matched filter. And we can see, so in the previous slide, we defined the channel estimation error variance as delta H square. Then in the multi-user efficiency of the traditional filter, we can see the channel estimation error variance impacts the denominator of this expression. And the same, we can have the same conclusion for the matched filter, because we can see here the channel estimation error variance impacts the denominator. It makes the variance, it makes the multi-user efficiency smaller. But for LMMSE, the analysis is kind of more complicated. And we can obtain such an interesting conclusion. Suppose eta bar is the asymptotic multi-user efficiency with perfect channel state information. Then the asymptotic multi-user efficiency with imperfect channel estimation is given by this expression. Here the constant C is the ratio between the channel estimation error variance over the noise power. When the noise power turns to 0. Then if the noise power turns to 0 and the channel estimation error variance is of larger order of the noise power, then the AME could be 0. That means if we have a channel estimation error, the performance of the LMMSE multi-user detection could also be inefficient, but you cannot help more. Then next we consider the systems without channel state information, because in a wireless system, actually you have no channel estimation, you have no channel state information at the very beginning. So even if we suppose that the number of paths and the path delays are well known, we still cannot obtain the perfect channel state information. First, we have thermal noise. This will add some error to the channel state information. Second, we may have interference. Even if we don't have thermal noise or we don't have interference, since we have only limited number of pilots, you still cannot get perfect channel state information. The only way you can get perfect channel state information is there's no noise, no interference, and you put all the symbol transmitted on the subcarriers or pilots. But that is pointless because that conveys no information. Then we need to estimate if we tackle the intercarrier interference using the spreading code approach, then we need to estimate many channel coefficients in this expression. For traditional filter, we only need to estimate the diagonal elements, so that will remove a lot of estimation. But for LMMSE multi-user detection or matched filter, we need to estimate the whole spreading code. Then this will be prohibitively hard for a practical system. But we need not to estimate all the elements, because actually the power is quite concentrated on the desired subcarrier and its two adjacent subcarriers. So here we plotted the power distribution of a typical OFDM system. So this axis is the proportion of the power. This is a CDF. And we can see for subcarrier 0, that is, for example, if we are detecting the signal of the first user, then on the subcarrier 0, actually most of the power is focused on this subcarrier. And some of the power is within the adjacent subcarrier. As for the more As for the subcarriers further away, we have a very little power there. Then why should we bother to estimate? Why should we bother use the information on those subcarriers? Because there are very little power on those subcarriers. Then we can truncate the spreading code. Because, we can approximate the spreading code matrix by a cyclic band matrix. We can truncate all those elements. We can keep, for each column, we can keep only 3 elements. That is the diagonal elements and the 2 adjacent elements of the diagonal matrix. Because we know most of the power are focused on these elements. Then we can remove most of the estimation of most of the elements within the spreading code matrix. We can reduce the number of unknowns from n times L. N is the number of subcarriers. L is the number of paths to 3L. Suppose we have, say, 2 paths, and the number of subcarriers is, say 1024. Then we can reduce it from 1024 times 2 to just 6 unknowns. And we will see such approximation does not make much performance degradation.
So I wonder,
yes.
Answer a question. When I think of multi-user detection, I think of something that can separate overlapping signals regardless of their overlap. But when I think of something like frequency domain equalization, what it does is it applies local calculations. It would just try to use the adjacent frequencies to reduce the ICI. So if we're going to limit things to just the adjacent frequencies, then what's the distinction between frequency domain equalization and multi-user detection?
I guess the ideas behind both approaches should be the same.
Could the algorithm?
Yeah, that is possible. That is possible. But maybe finally we can show that actually from the viewpoint of multi-user detection and from the viewpoint of frequency domain equalization, and they will reach at the same point finally.
So it's possible then that you're really looking at traditional techniques, but from a multi-user perspective. It may be that there's not a new algorithm.
That is possible, because we need to study, we need to do more research to see if both algorithms can match each other. But it is also possible that they are different, because we are looking at the same problem from 2 different aspects. So maybe in our next step, in our next stage of research, we will consider the traditional frequency domain equalization to make a comparison here.
Yeah, because that matrix, if you look at it, it has a circular convolution.
Yes, exactly. Yeah.
Where the taps are fixed from one symbol to the next. So that's a filter.
Yeah.
in frequency,
Yeah.
Which is the same as frequency domain equalization.
Okay. So you mean in the frequency domain equalization, actually you're also using a linear detector, and then you're also using the LMMSE criterion.
Yeah, I think it's possible.
Yeah, that is possible. Yeah.
The other scenario for linear polarization and
Yeah.
actually they are similar.
Yeah.
Oh, okay.
Yeah.
But I think at least it's also interesting that the 2 literature can kind of converge, because
Yes.
there are many interesting results from the multiuser detection literature in terms of like asymptotic efficiency and but random matrix maybe doesn't apply here. But I mean, these are not studied in the equalization literature. So there might be some cross-fertilization here.
And actually, we can apply a lot of existing conclusions in multi-user detection community. Suppose, for example, the multi-user efficiency, the expression for the multi-user efficiency, or asymptotic multi-user efficiency. So that is only defined in the multi-user detection community. And we have a lot of existing conclusions. And then we can just apply those techniques or those conclusions to the OFDM system. And that will reduce a lot of work. And as we can see, we have obtained a very interesting for the asymptotic multi-user efficiency for the LMMSE multi-user detector. That is the asymptotic multi-user efficiency is a ratio of the harmonic mean and the arithmetic mean. So that may not have been obtained from the viewpoint of equalization. So let's go on with the slides. So here we have truncated the spreading code matrix. But the problem is how to estimate the spreading code matrix, the truncated spreading code matrix. Only 5 minutes? Sure. Maybe 5 more slides. Then we can set P in the frequency in the subcarriers. We can set P pilot clusters, and in each cluster, it contains 3 consecutive pilots. For example, if we have a system with 512 subcarriers, I suppose the number of pilot clusters is 20, then the overhead is just 12%. So that is not a big deal in a practical system. And we can put the pilots in this way. This is information symbols. This is pilot clusters, and then information symbols, then pilots. We can interleave the information symbols and the pilot clusters. And we consider only the output at the center of the subcarriers. See, if we have only 3 pilots, we can consider only the output at this pilot, and this pilot. And the output of these pilots are given by these equations. Group of equations, and we can solve these linear equations. If the number of pilot clusters is larger than 3L, that is the number of unknowns, then we can use just a few pilots to estimate the unknowns in the spreading code matrix. So next, I will give some numerical results. Suppose in the system we have 512 subcarriers. The OFDM symbol period is only 0.1 millisecond. The carrier frequency is just 5 gigahertz. And mostly we focus on the frequency flat fading. If we consider multipath, we consider only 2 paths. And we use Jake's model for generating the fading process. Actually, we are using the 3GPP2 CDMA 2000 evaluation method to generate the fading process. Then we can take a look at this figure. It looks a little bit vague. So this is the performance of the frequency flat channels when we have perfect channel state information. This axis is the multi-user efficiency. This axis is the CDF. And we can see the LMMSE multi-user detection, the performance is here. So that means the multi-user efficiency is very close to 1. And we consider 2 cases. One is SNR is equal to 20 dB, and the other one is SNR is equal to 30 dB. We can see in both cases the multi-user efficiency of the LMMSE multi-user detection is very close to 1. And when the SNR is 20 dB, the performance of the traditional filter and the matched filter is given here. Both are worse than the LMMSE multi-user detector. When the SNR is equal to 30 dB, it is much worse for the matched filter and traditional filter. So we can see in this case, LMMSE multi-user detection is very good. Then, if we have frequency selective fading, actually we can draw very similar conclusion, because LMMSE multi-user detection is the performance of the LMMSE multi-user detection is here. It's very good. And when the SNR is 20 dB, this is the traditional filter and this is a matched filter. Both are worse. When the SNR is 30 dB, both the traditional filter and the matched filter are worse than the LMMSE multi-user detector. And another interesting observation is the matched filter is worse than the traditional filter. And actually matched filter is almost the worst in all three types of multi-user detectors. And as for the case without perfect channel state information, we use truncated spreading code. Then we can see when the SNR is only 20 dB, the traditional filter is the best. Because in LMMSE multi-user detector, we need to estimate a lot of unknowns. And that will cause the performance worse. But when the SNR is 30 dB, the LMMSE multi-user detection is the best. So that means in the high SNR regime, even if we don't have a perfect channel state information, LMMSE is still better than the other two types of multi-user detectors. And actually here, the matched filter is still the worst detector. Then we can draw conclusions. First, we have learned that there exists ICI in the OFDM systems if the channel is time varying. And we can convert a OFDM system into an equivalent CDMA system. Then we can apply the technique of multi-user detection to suppress the ICI. And finally, we can say the multi-user detector will never die. So that's all for my presentation. So any questions?
Let me seek some questions from the remote site now. Okay, I guess there are no questions. Let's go back. Let's go back here. Are there any questions? We have time for a couple questions. Any questions?
So can I understand that actually, if we can convert the OFDM system into an equivalent CDMA system, actually the problem seems like more benign as compared to the multi-user detection problem in the traditional CDMA case. Because in this case, we only first the powers are highly unbalanced, right? So most countries on the desired carrier and maybe two adjacent carriers. And we always have a load one system. We never encounter an overload system, right?
Yes.
So in such a system, seems like linear MSE should perform quite well. We don't need to further explore other like non-linear multi-user detection technique. That's my intuition. I'm not sure. Do you have any comments here?
So you mean?
I think in this scenario, I think linear MSE might perform like close to optimal, or not far away from optimal, right? In such a kind of scenario.
So here the problem is we don't know the performance of the optimal one.
Mm-hmm.
Because it may be very difficult to analyze the performance of the optimal multi-user detection. Because in traditional CDMA system, we can use the large random matrix theory or the replica approach in statistical mechanics. But here we are losing the independence of the elements in the spreading code. Then that will, I guess, maybe that is intractable in math.
So can we have at least like brute force?
Brute force. But here the problem is for a practical system. Usually the number of subcarriers is 512. Then for optimal multi-user detection, we need to compute a term of very huge term that is 2 to the 512. exponential terms. At least I cannot wait for such a long simulation. It will never end before I die. So anyway, that is a very interesting research topic. Maybe we can find some proximate approaches to analyze optimal one. But I guess that is just for theoretical interest, because it may not be useful for practical systems. And actually, my work is just from academic curiosity. I just want to see if we can apply the multi-user detection to other vector channels. So yeah, that may be interesting. Maybe we can apply approach of replica method to try to see if we can still have replica in the OFDM system.
All right. Well, let's thank our speaker again.